Hello again. Today we're looking at how we can test if two events are independent from each other using relative frequency. That means rather than actually knowing what the probability of the two events are, we'll use observed data to find out whether the two events are independent of each other or not. This has got lots of real world applications, and the example that I've got for you today is about like vaccine effectiveness. So how well the flu vaccine works in this example. And I know that some of you will be pretty interested in that. It's a pretty interesting topic. Now, so in this example, research laboratory wants to investigate the effectiveness of a flu vaccine. So it's doing a study. It follows 150 randomly selected people from a community and notes if they received a flu shot prior to the flu season and records their health outcome over the season. So some people will get the flu shot, some people don't. Who's going to get sick? Are you going to be more likely to get sick if you got the flu shot, or are you going to be more likely to sick if you didn't get the flu shot? Well, we've got the results of the study just there. And then in the red box there, the little formula box, I've got two important formulas. So we can say that the two events are independent if either of these things are true, really. So either the probability of the first one happening, given the second one took place, is just equal to the probability of the first one happening. So in our case, that would mean the probability getting sick, given you had a flu shot, was the same as the probability that you got sick. That would indicate the two events were independent. It didn't matter whether you got the flu shot or not. You still got sick with the same probability. Or the probability that you got sick and got the flu shot was equal to the probability that you got sick multiplied by the probability you got the flu shot. Okay, so that's the other way that you can test for this, and this is just a rearrangement of the formulas that we've got there. Doing one of these things would be enough, but I'm going to do them both just to show you what's going on with this. Okay, so let's start with the first one there. We need to identify the probability that a person got sick given they had the flu shot. So I would say we're probably looking, all right, they got sick given they had the flu shot was 12, yeah, out of 75, right? So I'd say that first one, A given B, yeah, probability they were sick given they had the flu shot, yeah, is equal to 12 out of 75. It might be helpful in this kind of question because we've got different totals going around. So it might be helpful to just work out our probabilities as decimals. I mean, you can express a probability as a decimal, a fraction, or a percentage. So I'm just going to do these as decimals. So I'll grab my class pad. I was hoping this would be far enough out of the way that it would give me access to all the buttons. Right, here we go. So we've got 12 divided by 75. Right, a decimal here of 0.16. That's 0.16. All right. Is that equal to the probability of someone getting sick in general? Well, let's have a little look. The probability someone will get sick in general is 37 people in total got sick out of the 150 participants in the study, the randomly selected people. Okay, so we do probability of getting sick is equal to 37 out of 150. And again, I don't know off the top of my head whether that's more or less likely than 12 out of 75. So I'm just going to express it as a decimal so I can compare them easily. So 37 divided by 150, 0.24. Oh, there's a bit more going on there, wasn't there? 247, we'll call it. Well, let's just call it 2.5. Right, it's two decimal places, and then we can compare them. Right, 0.25 is definitely more than 0.16. It's actually, if you look at this, 0.25 is an extra 0.09 more than 0.16. So it's more than 50% greater. You've got more than 50% greater chance of getting sick without the flu shot than if you have the flu shot. So we would say that was a significant difference. Now, before I go any further, what I would say is there is some more complicated maths around how we decide whether a result is significant or not. And you'll learn that next year at the end of the Year 12 methods course. So you can test for significance and statistical significance using the normal distribution and a bunch of complicated maths that you'll learn next year. For now, just eyeball it. If it's for this exercise that you're going to do today, just if the two things are the same to within 0.01 or something like that, then they're the same. But if they're like this one, half a gain, more than half a gain, then they're different. Okay, so you'd say that was enough to say that they're not independent, and so getting the flu shot makes a difference. The other way that you could do this, we could use the other formula. I'm just going to go down there, right? We could use the other formula, the probability of A intersection B equals probability of A times probability of B. If that is true, then the events are independent. And remember, in this case, if the two events are independent, if getting the flu shot is independent from getting sick, that means the flu shot doesn't do anything. It means there's no effect of getting the flu shot on whether you get the flu or not. Okay, so let's test it out that way. The intersection of A given B in our case is the probability of getting sick and getting the flu shot, right? And again, I think that is sick and the flu shot. That is still those 12 people there, isn't it? Yeah. And it actually, in this case, would be 12 out of the 150. So slightly different probability. That equals 12 out of 150. And just again, because we're going to have some different totals floating around maybe, to make this easy to compare, I'll just run it off as a decimal. So 12 divided by 150. I bet a bunch of you in your head are saying, well, that's going to be half of 12 over 75, which is 0.08. Brilliant. You guys are so smart. I've got to check on my class pad to make sure I'm right a lot of the time. Okay, so 0.08 is the probability of the intersection. Now, if I do the probability of getting sick, which is 37 out of 150, and I multiply it by the probability of getting a flu shot, which is 75 over 150, I can compare the two and see if they're the same, can't I, right? If they're the same, then we have independence, which means the flu shot doesn't do anything. So, probability of getting sick multiplied by the probability of getting a flu shot equals, I'm going to scroll this up so I don't have to write on my own face. That equals, probability of getting sick is 37 out of 150 multiplied by how many people got the flu shot? 75 out of 150. All right. And that equals, I'll bring up the old class pad again. So 36. Let's try again. This thing's gone a bit glitchy. Okay, class pad 37 out of 150 multiplied by 75 out of 150. And what does that come to? 0.12333333333. 0.12333 recurring. Okay, and again, are these the same? Is 0.08 the same as 0.123 recurring? And given that we're dealing with actual observed data, might not be exactly the same. So you're going to go, are they roughly the same? I would say they're not. 0.123 recurring is more than 50% greater than 0.08. It's quite a big difference. So definitely statistically significant, that difference. And remember, you'll do proper work with proper statistical significance in year 12. But for today, that's where we're at. We'd say that not independent, therefore flu shot is effective. Okay. Well, that's a relief, isn't it? Couple of things to think about here that go a little bit outside of just the maths of doing this. We've got the word random there. People were randomly selected. This is an important notion, because you don't want to get bias in your sample if you're going to do this kind of work. So random selection is important. This sample size of 150 might not be big enough. Maybe if you took a bigger sample, you might get a different result. Maybe we just, with 150 people, there is a chance that we've introduced some bias just accidentally, even though we've got a random selection of people. So that's some thoughts about how we conduct these kinds of standardized random trials. Okay. Enjoy. Thanks for listening to the video, watch the video, and good luck with the task.